Now let's look at operations with power series. So let's say that we have two different functions. We have f of x equals the sum from n equals 0 to infinity of a sub n times x to the n. So for this guy right here, what we're saying is that a sub n here, this is my formula, and remember it's a power series, so you have an x to the n as part of it. And then g of x is equal to the sum from n equal 0 to infinity of b sub n times x to the n. And in this guy, b sub n again is your formula, and again power series, so that's why you have an x to the n. So you have three different things here. The first two are very similar because both of them deal with composite functions. The first bullet point says that if you have f of k times x, and this is where k is equal to a constant, then you could rewrite this series right here as, well, instead of x, you'd write k times x, distribute your power of n, and then you'd have whatever your formula is times k raised to the n times x raised to the n. The second one is very similar because again it's a composite function. It's not x, it's x raised to a power. Here n is also going to equal a constant. So if you're trying to find f of x raised to the nth power, it's going to be the exact same thing that you have, but your x to the n now gets raised to that nth power. So for those composite functions, when you're multiplying x by a number or raising x to a number, we're just going to be plugging in whatever we have here, k times x or x to the n, in place of this x here in the original, and then expanding out when we're finding our power series. The last one is f of x plus or minus g of x. So if you want to find f of x plus or minus g of x and you're given two different series, the first thing that's really important is they got to begin at the same spot. For example, these two given series both begin at n equals 0. If the series have the same starting point, then the sum or difference is going to be a sub n plus or minus b sub n times x to the n. So you're going to take whatever your a sub n is and add or subtract it to whatever your b sub n is to find your new formula. Now the interval of convergence for this last bullet point is different. What it's going to be is the intersection of the interval of convergence of the two original series. What I mean by that is if the interval of convergence for f was, let's say, from negative 1 to 2, and then the interval of convergence for g was from 0 to 3, you could think of it as a number line here. Negative 1, here's 0, here's 2, and here's 3. If the first one had an interval of convergence from negative 1 to 2, so it was all those numbers, and the second one had the interval of convergence from 0 to 3, so it was all these numbers, the intersection is going to be what they have in common. So that would mean that the intersection or the interval of convergence of the new series there when you're adding or subtracting them together would be, in this random example I just made up here, would be from 0 to 2 because that's their intersection, that's what they have in common. Now what we're going to do is use these operations with power series, and we're really going to stick to the first two. It's telling us that we know that we have this power series, and our power series is 1 over 1 plus x is equal to the sum from n equals 0 to infinity of negative 1 to the n times x to the n, where the absolute value of x is less than 1. Notice that's exactly what we got for this guy right here because it's number 4, and we got the exact same thing, and we knew that that absolute value of x had to be less than 1. So what we want to do is we want to use this formula to find a power series centered at 0, and then again determine that interval of convergence. So we're going to do number 5 again. Well, number 5 we already know what it is, but we wanted to rewrite it a different way. If we had, let's call it g of x equal 1 over 1 plus x, the difference between my function here and this function here is that this guy here is an x and this guy here is an x squared. So if f of x is equal to g of x squared, we would then write 1 over 1 plus, well, this x would become x squared. Basically, what we can do is say, hey, if I already know what this formula is, then it's just going to be the sum from n equals 0 to infinity of negative 1 to the n, but then instead of writing this x, I have to write x squared and then raise it to the nth power. And if we distribute that power to power, like we were talking about before, then this is just the sum from n equal 0 to infinity of negative 1 to the n times x to the 2n. And if you go back to example 5, that's the exact same series that we came up with doing it this way over here. Now what about that interval of convergence? Well, same thing. It's telling me that the absolute value of x has to be less than 1. So we take this guy here and say the absolute value of x squared has to be less than 1, which we already learned how to solve in example 5. And we know that that would just be an x squared minus 1 less than 0. And then that interval of convergence was negative 1 to 1. We'd actually have to solve that exactly like we did in example 5. Since we've already done it, I won't waste our time going through it again. But what we're allowed to do is use this composite function to very quickly figure out what the power series is and then quickly help us figure out what the interval of convergence is. So let's look at number 6. As I said, we know this guy. We know that g of x is equal to 1 over 1 plus x. But I don't have an x, I have a 25x squared. So really what we're looking at is that our f of x is really g of 25x squared. So that would make it a 1 over 1 plus 25x squared. So that means that this guy here is the guy that I'm plugging into that x. If we want it to be the series, this is going to equal the sum from n equals 0 to infinity of negative 1 to the n, because we're just copy pasting what our series is here, negative 1 to the n, but instead of the x, I write what was in those parentheses, and that's going to be 25x squared, and that still gets raised to the nth power. Well, I can leave it like that, or I can distribute that nth power. If we were to distribute the nth power, we're looking at the sum from n equal 0 to infinity of negative 1 to the n times 25 to the n times x to the 2n. And either this answer or this answer is acceptable. They're both correct. Alright, what about that interval of convergence? Well, that interval of convergence, remember, is going to be where the absolute value of x is less than 1. Well, we don't have an x this time. What do we have? We have a 25x squared. So where is the absolute value of 25x squared less than 1? Well, this is the same thing as the last time. This is one of those polynomial inequalities, so I have to get the 1 on the other side, 25x squared minus 1 less than 0, and find those x-intercepts. If I'm finding the x-intercepts, I have to set 25x squared minus 1 equal to 0 and solve for x. So if I add 1 and divide by 25, I have x squared is equal to 1 over 25. Taking the square root to solve, I get x is equal to plus or minus 1 over 5. Therefore, if we were to graph this, here at negative 1/5 and here at positive 1/5, I'd be crossing the x-axis. So my polynomial would look something like this, which means that if I'm trying to find out where I'm below the x-axis, it's going to be all the numbers between negative 1/5 and positive 1/5. Therefore, that interval of convergence is negative 1/5 to positive 1/5. What about our very last one? F of x is equal to the natural log of x plus 1. Well, wait a second. That looks nothing like this, right? That does not look like a 1 over 1 plus x. That doesn't look like a rational function. And that's what I need. So how do I get it to be a rational function? Well, what I'm going to have to do is I'm going to have to take the derivative, because what is the derivative of the natural log of x plus 1? Well, the derivative f prime of x here would be the derivative of x plus 1, which is 1 over itself, x plus 1. And now I look just like this guy, and I know exactly what that guy is. Well, then that means that we are looking at the sum from n equal 0 to infinity of negative 1 to the n times x to the n, because that's exactly what I have over here. Well, now that I have a series, I can go back to the original. Well, how do I go back to the original? Well, if I have the derivative to go back to the original, just like we did in section 9.8, we integrate. So in order to find the natural log of x plus 1, I'm going to have to integrate this. So when I integrate this guy right here, I know it's going to be c plus, And then it's the same here. It's that sum from n equals 0 to infinity. This guy here doesn't have an x, making it a constant multiplier. So negative 1 to the n. This is my x right here. So I know that I need to add 1 and then divide by that number. I'm dividing by n plus 1. So there we go. That is the series for the natural log of x plus 1. It's c plus the sum from n equals 0 to infinity of negative 1 to the n times x to the n plus 1 all over n plus 1. So I have my series, and now I need to find the interval of convergence. Well, the interval of convergence is going to be same thing as before, the interval of convergence here, right? Because that's still my r. It's got to be where the absolute value of x is less than 1, which we know is just negative 1 less than x less than 1, or negative 1 to 1. But we found this guy by integration. We didn't find it by using the sum formula for our geometric series. Because we found it by integration instead of that sum formula, we will have to check the endpoints. So we are going to have to check the endpoints in order to find the interval of convergence because we integrated. Now let's check them. Let's check x equal negative 1. If I check x equal negative 1, I have the sum from n equals 0 to infinity of negative 1 to the n. Instead of this x, I write negative 1 to the n plus 1 all over n plus 1. Well, here my bases are the same, so I add the exponents, and that gives me the sum from n equals 0 to infinity of negative 1 n plus 1 is 2n plus 1. What is that? Well, that's an odd number, and if I'm raising a negative 1 to an odd number, it's always a negative 1. So I'm going to pull that negative 1 out of the summation and just leave myself with 1 over n plus 1 on the inside. Now I have to figure out what happens to that. What happens to the sum from n equals 0 to infinity of 1 over n plus 1? Well, let's do a comparison because it's not a known series, and let's compare it to a 1 over n. That's a p series. P is equal to 1, therefore I know it's going to diverge. Let's do a limit comparison test. So the limit as n goes to infinity of the given 1 over n plus 1 divided by the known, or times the reciprocal of the known. Then we're looking at the limit as n goes to infinity of n over n plus 1, which n over n we know is going to give us 1. And it's the limit as n goes to infinity of 1, which is 1. Therefore, by that limit comparison test, our series diverges. So the series here diverged because with the limit comparison test, we ended up with a finite positive number, which means that whatever the known series did, the given series also did. So I've checked x equal negative 1. I'm not going to converge there. I'm going to diverge. Now I have to check x equal positive 1. So let's grab x equal positive 1 and check that guy. If I check x equal 1, we're looking at the sum from n equals 0 to infinity of negative 1 to the n, and then that would be a 1 to the n plus 1 all over n plus 1. Well, a 1 to the n plus 1 is just going to be 1, and if I'm multiplying by 1 when I'm adding infinitely, we can ignore it because it's the multiplicative identity, so I don't worry about that guy, and I can just rewrite this as the sum from n equals 0 to infinity of negative 1 to the n all over n plus 1. Well, what is this? That's an alternating series. Since it's an alternating series, I can jump to the alternating series test. So I take the absolute value of a sub n, which is going to be a 1 over n plus 1. Now what's the limit as n goes to infinity of 1 over n plus 1? Well, that's going to equal 1 over infinity, which is 0. The first part of the alternating series test has been met. The second part, a sub n plus 1 has to be less than or equal to a sub n. So a sub n plus 1 would be 1 over n plus 1 plus 1, or n plus 2. Is that less than or equal to a sub n, which is 1 over n plus 1? I'm not sure. Cross multiply. Is n plus 1 less than or equal to n plus 2? Absolutely. Therefore, by that alternating series test, our series converges. Since the series converges, we know that at 1, we're going to include the number, and since at negative 1 the series diverges, we won't include that number. Therefore, the interval of convergence there is negative 1 to 1, not including negative 1, but including 1. If we think about this one graphically real quick, just like we looked at our last ones, y equals the natural log of x plus 1. And then for our other one, we have y equals the sum from n equals 0 to, and let's give it a slider, a. And then what we said it was negative 1 to the n. And then it was times x raised to the n plus 1 all over n plus 1. Now notice, let's make this go to 100 again, that as we get closer and closer, this green graph wanted to be the blue one, and it's centered at 0, and that interval of convergence is from negative 1 all the way to positive 1. That's it for representations of functions as power series.